For this video, we are going to be discussing special right triangles. So there are two specific types of right triangles that we're going to be considering to be special right triangles. And they are the 30, 60, 90 right triangle. It's named that way because I have one 30-degree angle, one 60-degree angle, and one 90-degree angle. And the isosceles right triangle, which we can also think of as the 45, 45, 90-degree right triangle. It has two 45 angles and a 90-degree angle. These triangles have special properties, special relationships between their side lengths, and we can use those relationships as sort of shortcuts to solving for missing side lengths if we're given some of the information. So you can write these down and see what they are, and we're going to go ahead and come up with them on our own right now using the Pythagorean theorem. So first let's focus on the 30, 60, 90 right triangle. So I'm going to show you how to first build a 30, 60, 90 right triangle, and then we're going to come up with our properties. So to build a 30, 60, 90 right triangle, I'm going to start with an equilateral triangle. So in an equilateral triangle, we know that all of our sides are the same length. We also know that all of our angles are equal, and because all the angles have to add up to 180 degrees, we know that these angles are all also going to be 60 degrees. And that's important here. So what I'm going to do is I'm going to take and I'm going to draw the perpendicular bisector of this bottom side here. All right. If it's perpendicular, then we know that this angle is 90 degrees, and we know that this side length right here is exactly half of this side length. And because all of our sides are the same length in an equilateral triangle, this part here is equal to half of this side length here. We don't really need this whole side at all. This doesn't really matter to us. So this triangle that I've now created, let's name it A, B, C. ABC is going to be my 30, 60, 90 right triangle. And I know this because, well, here's my 90-degree angle. Here's my 60-degree angle, because this is equilateral. And because the triangles all have to add up to 180, then this is all, or the angles all have to add up to 180, then this has to be a 30-degree angle. All right. Now, we're going to call our shortest side, call it A, lowercase a. All right. So now, because we know that this is a perpendicular bisector, and A is half of this whole side length, then A is also half of this whole side length, so we can call this 2A. All right, so we're almost done. We're almost there. We're starting to put together our 30, 60, 90 right triangle. So now I need to find this other length over here. Well, to do that, we're going to need the Pythagorean theorem. Okay, so Pythagorean theorem tells us a squared plus b squared equals c squared, where a and b are the two legs of the triangle, and c is the hypotenuse of the triangle. So let's just substitute in some values here. Well, a we know is a, that's fine. B, we don't know b yet, let's just leave it as b. But c, we know, is equal to 2a. Okay, so it's 2a squared. Well, if we square 2a, we're going to end up with a squared plus b squared equals 4a squared. 2 squared is 4, a squared is a squared. All right, so now let's just solve this to figure out what b equals. We can subtract a squared on both sides, and I get b squared equals 3a squared. And then if I square root both sides, well, this side I just get b. Over here, the square root of a squared is a, and the square root of 3 doesn't simplify, so we just leave it alone. A times the square root of 3. And that is our length of our other leg. It's a square root of 3. And there we go. We've derived the side lengths of a 30, 60, 90 right triangle. The shortest side is a, the hypotenuse is 2a, and the other leg is a times the square root of 3. We're going to be able to use this here in a minute to be able to solve some problems for missing side lengths. But first, let's talk about a 45, 45, 90 right triangle. So 45, 45, 90 degree right triangle, we know, is going to be an isosceles triangle, right? Because our base angles are equal, which also tells me that my side lengths are equal. Okay, so if my side lengths are equal and I call them A, all right, I've got two legs that are both A, and now I need to find the hypotenuse. Well, that's pretty easy. Okay, once again, if we use Pythagorean theorem, a squared plus b squared equals c squared, except we know that a and b equal each other, so I could say a squared plus a squared equals c squared. Well, adding a squared and a squared gets me 2a squared equals c squared. Square root to both sides. Square root of a squared is a. Square root of 2 doesn't simplify, so it's square root of 2. And so I have a square root of 2 equals c. So my third side is a times the square root of 2. That's all there is to it. So now we've figured out exactly how to come up with our special properties of these special right triangles. Now, do you really need these special right triangles? Not necessarily, not if you know the Pythagorean theorem, but they do make a really good shortcut in the event that we need to find a missing side. So, let's do that. Example 1 says, using the information in the picture, find the missing side lengths and angles. Okay, so I've got a right triangle, and I know one of my angles is 30 degrees. So that means the other one has to be 60 degrees. So I'm working with a 30, 60, 90 right triangle. Okay, so if I pull up the template of what a 30, 60, 90 right triangle looks like, okay, I know that the side across from 30, that's my smallest side. That's like x. Then I know that my other leg is equal to x times the square root of 3. So in this case, well, if we know that this is 6 and this is 6, then y is just going to be 6 times the square root of 3. Pretty simple. Then we know x is equal to 2 times our shortest side, so that's just 12. And you can see how this is a shortcut so that we don't really have to use the Pythagorean theorem. And in this case, we couldn't use the Pythagorean theorem because we have two missing variables. We'd have to use trig ratios, which we'll get to in a later video, and this makes it just a really easy shortcut. All right, example 2, once again, says use the information in the picture to find the missing side lengths and angles. Okay, well, I've got a 45 degree angle here, which means that this is also a 45 degree angle. And then that tells me that this is isosceles, so I know those two are equal to each other. So if I pull up my template, I know that my hypotenuse is equal to x times the square root of 2 if my other two sides are x. Okay, so 16 equals x times the square root of 2. Okay, so let's talk about this. How to solve for this? Well, to find x, we know we're going to divide both sides by the square root of 2. Okay, so I end up with 16 over the square root of 2 equals x. This is a problem because we do not want to have this radical down here in the denominator. We got to find a way to get rid of it. And one way we can get rid of that is by multiplying just this side by square root of 2 over square root of 2. Now hopefully you realize that square root of 2 over square root of 2, that simplifies to 1. Okay, and by doing this multiplying, these square root of 2's are going to cancel each other. Well, that's not what's going to happen. Sorry. Okay, when I multiply these, what I end up with is on top I end up with 16 square root of 2. 2 square root of 2 times 16, 16 square root of 2. And on the bottom, square root of 2 times square root of 2 is just 2. All right? And then 16 over 2, well, that's 8. So this works out to 8 square root of 2 equals x. So this comes out to kind of a weird looking answer. So maybe we want to check this just to make sure. So we know from the Pythagorean theorem that x squared plus x squared equals 16 squared. Okay, so we know that that's 2 times x squared equals 16 squared. All right, if we substitute in what we just got for x, 2 times 8 square root of 2 squared equals 16 squared. That's 2 times. All right, we can just split this up. 8 squared is 64. Square root of 2 squared is 2. And 16 squared is 256. If we do this multiplying on this side, we end up with 256 equals 256. So it does work. So our answer is simply 8 times the square root of 2. So now you can see how we use the special properties of our special right triangles to find the missing side lengths when we're given some information.